The fourth matrix operation is to take the transpose. That's a flip, taking the matrix and flipping it around the diagonal. It takes an m by n matrix and it turns it into an n by m matrix, and we write a superscript little t for transpose. And another way of saying it is that it just interchanges rows and columns. Rows become columns. So the transpose of a ij is equal to a ji. So what that looks like, here's a transpose. Take 3, 2, 1 as the first row. Now it's the first column. 3, 2, 1 going down. And 4, 5, 0, second row. Now it's the first column going down. The next is a big one. It's the determinant of a matrix. Now this is only defined for n by n matrices. So matrices that are square. And it takes an n by n matrix and it gives a scalar. A determinant of A is an element of the real numbers. Now I'll start with the fancy definition, and then I'll show you how it works. It's a sum. The determinant of A is the sum from j equals 1 to n. Remember, n is the size of both the number of rows and the columns. You have to do an alternating sum. That means you're going to have a negative every other term, and it's -1 to a power. In order to make that alternating, you start with j plus 1, so it'll start with a positive. That'll be 1 plus 1, so -1 squared is 2. And then it'll be -1 cubed, and then -1 to the 4th, and so on. What you do is you take the A1j entry. So that's the first row and the jth column, and j goes from 1 to n, so you're going down the column. You take each entry of j, each entry of A as you go down that first row and go down by columns. You multiply it by the determinant of M1j. Now, M1j is a matrix made from the original A by deleting the first row and the column j that you're in. It's recursive. In other words, you have to take the determinant now of a smaller matrix. That means that you'll use the same formula over again, but it has to stop somewhere. So we need a smallest version after you delete far enough so that you're down to just a single number. Then the determinant of a number c for a scalar c, thinking of it as a 1 by 1 matrix, is itself. You just get back c. So here, let me show you how that works with an actual matrix. So here's a square matrix, 3 by 3. So n equals 3. K will go from 1 to 3 in the sum. So we'll take the first row, 3, 1, 2. We'll start with the sum, and we'll have 3 terms at first. And it'll be -1 squared. The first one was to the 1 plus 1. And then take the entry in A, 3, and then the determinant of, and we get rid of the first row and the first column since we're in that. And we have the smaller matrix, 5, 6, -3, -1. Then the second entry is -1 cubed, and then that'll turn into a -1. The entry is 1, and if you delete that column and the row, of course, then what you're left with is 4, 6, 0, and -1. And then finally, the third entry is that 2, but now we're at -1 to the 4, since it'll be the plus 1 of that third entry, so 3 plus 1 is 4. And 2, since it's the entry, is 2. And then deleting that last column, we're left with in the first row, we're left with 4, 5, 0, and -3. All right, now we have to redo that process on each of those smaller squares. So each time we'll have a sum of 2 things, because there's n is equal to 2 for the smaller square. So I'll simplify a little bit as I go. -1 squared is 1 times 3, and then -1 squared again, because now we're using the definition again on this smaller matrix. The entry is 5, and the determinant of this if you delete the first row and the first column of the smaller matrix, is just the number -1. But I'll write it in there so you can see the process. Yeah, I'm sure if you've done this before on a 3 by 3 matrix, then you could probably go faster than me at this point. but I want to show the whole process so that you can see it no matter what size matrix you're working on. The second term of the determinant of 5, 6, negative 3, 1 is negative 1 cubed, and then 6, the entry 6, times the determinant of negative 3. Then I went ahead and did the next whole big term here on this next line. Negative 1 cubed is negative 1. I have a 1, and then I start taking the determinant. So I didn't write the 1. I just wrote negative 1 cubed times 1, which gave me negative 1. So inside the determinant, I have negative 1 squared. That's going to become a 1. And then 4 times the determinant of negative 1. And then a negative 1 cubed, which is going to become minus, and 6 times determinant of 0. Then finally, as the determinant inside of this last small matrix is going to be negative 1 to the 4 is positive. So I'll have 2 determinant, and the determinant will be negative 1 squared, 4 times determinant of negative 3, and then negative 1 cubed times 5 times the determinant of 0. Now I'll go back through and replace all of the easily simplified things. For instance, in the first term I have 3, I have negative 1 squared, which is 1, I have 5, and I have determinant of negative 1, which is negative 1. The determinant of a number is just itself. And then negative 1 cubed, which is minus 6 times determinant of negative 3, which is just 6 times negative 3. So altogether, that first term there, you can see it in the original as taking 3 times, and then 5 times negative 1 minus 6 times negative 3. But it does follow the formula. Then I have a minus, which is minus 1, and then 4, turn that negative 1 squared into a 1, times determinant of negative 1, which is just negative 1. So get 4 times negative 1 minus 6 times 0. That minus comes from negative 1 cubed. And then finally, the 2 times 4 times negative 3 minus 5 times 0. And now going ahead and working out those actual numbers, I get 3 times a negative 5 plus 18, so 3 times 13. I get negative 4 and then minus 0, so just a double negative 4, so plus 4. And then 2 times a negative 12, so negative 12 there, so I get 39 plus 4 is 43, and then minus 24 gives me 19. Now, it is true that as a theorem, you get the same exact answer no matter which row I you use. So in general, instead of using row 1 all the way through, I could use this formula, which uses any row I. So it still has j equals 1 to n, since then I'll be able to go along that row. But I'm going along row I, so I'll put in negative 1 to the I plus j. So it might start off with a different minus, depending on which row you're on. And then aij is going to be the entry, and the determinant of mij, where I delete the ith row in the jth column of the matrix I'm working on. Again, recursively. So negative 1 to the I plus j, you can look ahead and see what that's going to be. It has a checkerboard pattern. The first one was 1 plus 1 is negative 1 squared, and then 1 plus 2 is negative 1 cubed. So anytime you have odd plus odd, it'll give you even. So in the odd row and odd column, you get an even number. Also, of course, even plus even gives you even. And it turns out you can also pick a column to use instead of a row. Now, so if A has a row of zeros or a column of zeros, just pick that. Then as you go down the sum of that row, you'll be multiplying everything by 0, and you can shortcut it quite a bit and just see that the determinant of A is equal to 0. Here's another shortcut. If A is triangular, now that means that either all the numbers above or below the main diagonal are 0. So it either has all zeros above the main diagonal or all zeros below the main diagonal. The main diagonal is the diagonal numbers that go from the upper left to the lower right. So in the example, the main diagonal is 3, 1, 2, -4 here. And then triangular means that on one side of that main diagonal, everything is 0. So this one would be upper triangular because it's all zeros below the main diagonal. In that case, the determinant of A just equals multiplying all the main diagonal entries, which you can see by taking the formula, starting with that 3, for instance, and then crossing out the row in the column, and then doing a determinant of the smaller one. And as you go down that column, the rest of them will all be 0, so you can just work only with that first term. Then as in the smaller matrix, when you cross off the first row and first column, and first row, then same thing, you'll go down the column again. So eventually you can just see that you just get the multiplication of the rows on the numbers on the diagonal. In this case, I get 3 times 1 times 2, 6 times -4 is -24. Next, more determinant facts and shortcuts.